Welcome to The Explainer. I am so glad you're here because today we are diving headfirst into the glowing, bustling digital world of computer networking. I want you to imagine a futuristic city, literally made entirely of light, where streams of data are just flowing perfectly along these smooth, illuminated pathways. I mean, every single email you send, every online game you play, every website you visit, it all relies on billions of tiny pieces of information zooming through this network flawlessly. It's a total marvel of modern technology. It usually works so well we don't even give it a second thought. But in this seemingly perfect digital world, occasionally something goes wrong. Picture this. That smooth, glowing environment we just talked about, suddenly interrupted. A tiny glitch appears on the pathway. The lights flicker, and maybe a monitor somewhere in the real world distorts for just a fraction of a second. So what if one tiny mistake in a computer message could cause a massive problem? Now, I know that sounds like the plot of a sci-fi movie, but in the realm of computer science, the stakes of a single digital glitch in a smooth network are incredibly high. The entire system relies on absolute precision. Okay, let's dive into this. What exactly causes this micro disaster? Well, at the very core of all this data are bits, zeros and ones. They're the fundamental building blocks of literally everything digital. But sometimes, as these streams of binary code are flowing smoothly across the digital pathway, a glitch strikes. It's called a bit flip, and a bit flip is exactly what it sounds like. A single bit actually changes its color and flips from a 0 to a 1 or a 1 to a 0 right in the middle of transmission. You might be wondering, why on earth does this happen? The source material points out two main culprits. First, everyday physical obstructions or radio waves can cause Wi-Fi interference. And second, a sudden power surge, like a temporary spike in electricity from a lightning strike, can jolt the hardware just enough to flip that bit. And this really illustrates the fallout. When a bit flips, you might see this glaring red error pop out of a perfect sea of blue binary code. Files can distort, icons might flicker, and your data basically becomes corrupted. But hey, it's not just about a pixelated image on your screen. We rely on computers to send data accurately across networks to run some of the absolute most crucial infrastructure in the world. Even a tiny error, literally a single digit out of billions, can create massive ripples and serious problems in important systems. To really ground this abstract concept, let's look at a terrifying real-world scenario straight from our source material. Big skyscrapers often use network-connected carbon monoxide and heat detectors to keep everyone safe, right? Imagine a fire starts in a room. The heat detector senses it, does its job, and sends a binary message to the main security computer. But on the way, bam, there's a power surge. A bit flips. Because of that single flipped bit, what if the computer mistakenly reported that the heat detector was cold, completely ignoring the fire? That is how incredibly critical a single 0 or 1 can be in the real world. Fortunately, computers have some incredibly clever ways to find these mistakes before it's too late. So how do they check for mistakes? Well, they use a friendly, heroic little system called the Echo Check. It's basically a digital repeat after me game. Think of two computers, a sender and a receiver, just playing this game together. It's exactly like when a friend tells you their phone number and you repeat it back to them out loud just to make absolutely sure you heard it correctly. It is a super simple but highly effective method computers use to catch those dangerous bit flips before they can cause any real disasters. Let's move along and see how this builds step by step between our sender and receiver. It's a really clean, linear four-step process. Step 1. The sender creates and sends a glowing data packet across the digital path to the receiver. Step 2. Immediately upon getting it, the receiver catches the packet and echoes the exact same data back along that path. Step 3, the sender places the original message and the returned message side by side so it can compare them. And Step 4 is the final result. If they match perfectly, great. If not, the data has to be sent again. Now, what's really interesting about this process is how dramatic this mismatch can be when we look at the actual numbers. Let's say our sender transmits the binary number 00000001. In our normal everyday numbers, which we call den array format, that binary number represents the number 1. But on the way over, an error occurs. A bit flips at the very beginning of the sequence. So what the receiver echoes back is 100000000. In denary, that is the number 128. Think about that. Because of one tiny flipped bit, the message completely changed from a 1 to a 128. You can see exactly why the sender comparing these two streams side by side is absolutely vital. Which brings us to the strict golden rule of the echo check, straight from the source. If they match, there's no error. However, if they do not match, then the data is sent again. It is a completely binary decision, no pun intended. During that comparison phase we just talked about, if the bits match up perfectly, green lights flash, a check mark appears, and the system just moves on to the next task. But if there is even a single red mismatch, like our 1 versus 128 example, the original packet simply restarts its journey. The sender just throws out the bad data and tries again until it gets a perfect echo. However, every hero has a weakness, right? Think of our network as a pipe. When you send normal data, it uses a certain amount of space in that pipe. But with an echo check, you are sending the exact same data twice, once there and once back. This means a lot more data is being sent over the network, effectively doubling the bandwidth used for a single message. As the usage meter rises and that network pipe fills up, this extra traffic costs valuable time. Sending data twice uses more bandwidth and can really slow things down. And there is one final limitation to this system, and it's honestly a bit of a mystery. Let's say the sender compares the original data with the echo data and finds a mismatch. Okay, it knows an error happens, so it knows to resend the data. But it is completely impossible to tell exactly when or where the interference occurred. Did the bit flip on the initial journey to the receiver? Or actually, did the receiver get the correct data, but the bit flipped on the echo journey back to the sender? The system has literally no way of knowing. It just knows it has to start over. So as we wrap up this explainer, let's do a quick recap of the journey we just took. We saw how a tiny bit flip caused by Wi-Fi interference or a power surge can pose a massive danger to important real-world systems. We met the echo check, that handy repeat after me game that acts as our digital safety net. We watched the sender compare the data, and we learned the golden rule. If it doesn't match, resend it. Echo checks help computers catch mistakes, but they also take extra time and bandwidth. It's kind of comforting, really. Even incredibly fast, advanced computers have to take a little extra time to double-check their work, just like we do. So the next time you send a message, ask yourself, how many echoes did it take to get there perfectly? Keep that curiosity alive, and I'll catch you in the next explainer.